Hey guys, welcome back. Hopefully you were able to join our live class yesterday as we reviewed everything we learned in the past few weeks before a break in this, what are we on, chapter 4, talking about integration, what it means, fundamental theorem of calculus, things like that, some of the properties and rules. If you didn't get a chance to join that meeting, then just take it upon yourself to look through your notes, look through your recent homework assignments, just to get your juices flowing again. Today, we're going to talk about the second fundamental theorem of calculus, and I'm going to write FTC2 for abbreviation. And this is really just a shortcut for us. And it is used when we are finding the derivative of an antiderivative. Okay? So these first few questions here are an exploration on, well, let's take the antiderivative and then do the derivative of that, because that's really what it's asking for us to do. So in example 7, it says evaluate f of x when it's equal to this integral from 0 to x of cosine of t dt. Then find the derivative, okay? So when we integrate, and it's a definite integral, we are going from 0 to some x value. Well, the antiderivative of cosine is sine. So that's going to be the sine of t, and we have to evaluate it from 0 to x, okay? So the first fundamental theorem of calculus says that we can plug the x in, get sine of x, minus we plug our 0 in, sine of 0, which is 0, and we end up with the sine of x. So our function is the sine of x. And then it says, well, what's the derivative of it? Derivative of sine of x is cosine of x. So how does that relate to what I started with? Well, if I take the antiderivative and then do the derivative, it takes me back to where I started. So the second fundamental theorem says that if I'm taking the derivative of an antiderivative from a constant to x, I can just plug x in, and that gives me my answer, okay? Now, it has to be a constant because it doesn't matter if this ended up being a 0 or if it ended up being a 5, right? When I take a derivative, that constant becomes 0 anyway. So as long as that's a constant on the bottom, you can use this second fundamental theorem of calculus. So let's try it on your turn. Feel free to pause this and try it on your own, and then hit play when you're ready to see the answer. Okay, I'm going to show the long way, and then we'll start using our shortcut. Okay, understanding what the theorem actually does is how we're not going to make mistakes here. Okay, so your turn. Once again, pause if you want. It says that our function is the antiderivative of t squared plus 3t minus 1 from 0 to x. So we do our antiderivative, 1/3 t to the third plus 3/2 t squared minus t, evaluated from 0 to x. We plug our x in, get 1/3 x cubed plus 3/2 x squared minus x, and then minus, we plug our 0 in, and so that means our function is 1/3 x to the third plus 3/2 x squared minus x. Once again, it doesn't matter if we ended up with a constant other than 0 there. It says then find the derivative. So the derivative of this, and keep all this straight, when you're doing antiderivatives, derivatives, make sure you're doing the correct thing. So derivative, we multiply and reduce the exponent by 1. Antiderivative, we increase the exponent by 1 and divide. We do the opposite. Okay, so multiply by 3. It's now 1 x squared plus multiply by 2. It's now 3 x to the first minus 1. You can see how those are related. So the second fundamental theorem lets me go from this step to this step without all of the work. Okay? It says, going down there, right, in the box, if f is a continuous function on an open interval containing a, containing that constant, then for every x in the interval, the derivative of that integral is just f of x. Okay? So example 8. We'll do our shortcuts now. using the second fundamental theorem. It says, what is the derivative of this integral? Okay, it is a constant, that's good, okay? It's going to x, so the derivative of this integral is just going to be the square root of x squared plus 1. I'm done. I didn't have to do the antiderivative, which we didn't learn how to do yet, but I don't need to know that. The derivative of this integral, just plug your x in, okay? The second one, that was letter A. Letter B, the derivative of this integral from 0 to x of tangent to the fourth of t dt. Once again, I don't know what that is necessarily, okay, but because I'm doing the derivative, and we have a constant down here and an x right here, the second fundamental theorem says all I have to do is plug x in. I have that this is going to be the tangent to the fourth of x, okay? All right, now, this is where I was saying on the next page, this is why we need to understand what that second fundamental theorem is actually doing. It's providing for us a shortcut to jump to what the answer is without actually doing the antiderivative and then doing the derivative, okay? So, this next example 9, letter A, example 9, letter A says to find the derivative of this function. And this function is defined as the integral from pi over 2 to x to the third cosine of t dt. Okay, so let me show you what the long way would lead us to, and then see if you guys can figure out how we can adapt that second fundamental theorem so we can skip all of that work. Okay? The antiderivative for cosine of t is sine of t. We need to evaluate it from pi over 2 to x to the third. So we plug our x to the third in, minus, then we plug our pi over 2 in. Sine of pi over 2 is 1. So this is our f of x. What's the derivative? I need to remember all of my rules, okay? So the derivative, this would require the chain rule. The derivative of sine of something is cosine of something times the derivative of that inside, so times 3x squared. And then the derivative of 1 is 0. So what can you see that we could use to jump right from the question to the answer without doing that intermediate work? And this is where I wish you guys could respond to me. I'll leave you think about that a second. Well, the second fundamental theorem says that I should be able to just plug that in. Well, there's my cosine of x to the third. So that's partially right. But because it's not just x, because it's x to the third, you need to think of the chain rule, which means not only am I going to plug it in, I'm going to multiply by the derivative of that. If I multiply by 3x squared, I got my answer, okay? So we did have our constant down here. That's what's required for the second fundamental theorem. And then not only do I plug that function in, I also have to multiply by the derivative of that function because of the chain rule, because of what's actually happening in that work. Happening. Happening? All right, so let's try letter B. Okay, apply what we just saw here. So for letter B, it's saying that my function is the integral from 2 to x squared of 1 over t squared dt. And I'm supposed to jump right to the derivative, and trying not to spend all the time doing the antiderivative and then the derivative of that. It's not necessary. So the second fundamental theorem says, as long as I have a constant down here, I can take this x squared and plug it in. So that's going to be 1 over x squared squared, because it used to be t squared. We're replacing t. So x squared is going to get squared. But because that is x squared, we also have to multiply by 2x, the derivative of x squared. That's the chain rule part that we're considering, okay? We end up with 2 over x to the third, right? That's x to the fourth. Got an x on top. X over x to the fourth is a 1 over x to the third. There's a 2 there. That's my answer, skipping all of that work, okay? So, we even can do these problems if it's not a constant on the bottom because we can use some properties of integration. So here's our last problem. Last problem says that our function is the integral from negative x to 2x plus 2 of t squared dt. All right, I'm supposed to find the derivative of this integral. For me to use the second fundamental theorem, that has to be a constant, but it's not. So we got to do some things, okay? We can split this up to be from negative x to any constant we want to pick, okay? I'm just going to pick 2. Doesn't matter. Usually I pick 0. But let's go to 2 of t squared dt plus the integral from 2 to 2x plus 2 of t squared dt, right? So this is taking just a portion and another portion, and if you add those together, you get that whole length. It doesn't matter if the 2's in between or not, okay? Just pick some random constant. Where you leave off with the 1, you start back up with the other one. Now, it's almost set up. I can use the second fundamental theorem on this one, but not this one. I need to switch the limits of integration, okay? And when we switch the limits of integration, that makes that a negative. It's a negative. Now I can go from 2 to negative x. Okay. Both of them are set up. Second fundamental theorem says that you can plug the negative x in there. Okay, so this negative's here. Plug negative x in there. Negative x is going to get squared times negative 1, because that's the derivative of negative x, chain rule, times negative 1. Okay, so that's the first piece. Second piece, plug 2x plus 2 in there. 2x plus 2 is going to get squared times the derivative of that because of the chain rule, so times 2. All right, so I did my second fundamental theorem. I'm just needing to simplify this as much as I can. So we got a negative x times negative x is a positive x squared. Negative times negative is positive, so we get an x squared here. Plus, if we FOIL this out, 2x times 2x is 4x squared. Times 2 is 8x squared. 2x times 2 is 4x. There's going to be another one, so that's 8x. Times 2 is 16x. 2 times 2 is 4. Times that 2 is 8. Okay, combine like terms, and we end up with 9x squared plus 16x plus 8. And you might say, Mr. Wise, I don't believe you. Okay, well then you got to do it the long way. And you'll see that that is the answer. So real quick, this is where we'll end today. And then you guys have a small homework assignment just talking about the second fundamental theorem. Let's say that I was going to do this the long way. That means I actually have to take the antiderivative. The antiderivative is 1/3 t to the third. We would evaluate it from negative x to 2x plus 2. Okay, so we got to plug 2x plus 2 in there first. 1/3 times 2x plus 2 to the third. Okay, and then minus, then we'd plug our negative x in there. Okay. So you could try to simplify this if you want. I'd have to use maybe Pascal's triangle there. Or, I mean, this is my function. I could just take the derivative of it in this form because I know how to do that. Let me just work with it a little bit. I don't really need to multiply this out to figure out what the derivative of that is because I know the chain rule. That'll help me. But right here, a negative x to the third is a negative times a negative. That's a positive 1/3 x to the third. And then I can do my derivatives. So I multiply by 3, 2x plus 2 squared times the derivative of the inside, plus multiply by 3, I got x squared. And you see I'm right on this step right here. I'm going to end up at the same spot. Okay? FOIL that out times 2 plus the x squared, I end up with that answer. Okay, so I know I'm doing it right. Second fundamental theorem is used if you're taking the derivative of an integral. The top is some function, the bottom has to be a constant. If it's not, make it a constant like we did here, splitting things up. And once you get it set up, then the derivative of an integral, second fundamental theorem says, you can just plug your function in and make sure you multiply by the derivative of that function because of the chain rule. Okay? Good luck on your homework. Bring your questions to class. I'll see you next time.